Arratsaldeon, garaia iritsi zaigu, gaurko azkenengo hitzaldiaren hasierari eman diezaiogun, eta hori baino lehenago utzi egidazue labur bada ere, hizlariaren aurkezpena egiten. El profesor Herschbach enseña química en la Universidad de Harvard. Nació en San José, California, en 1932. Su iniciación al mundo universitario lo hizo en Stanford, en cuya universidad ingresó con una beca atlética, de jugador de fútbol americano en concreto. Pueden tomar esto como una premonición, ya que posteriormente, en el año 1986, le otorgaron el premio Nobel por sus trabajos en colisiones moleculares. Su experiencia como jugador de fútbol americano seguro que le fue útil en esto de las colisiones, campo en el que sigue trabajando profusamente. Sin embargo, el profesor Herschbach ha extendido su liderazgo a otras muchas áreas de la química y de la física, de hecho de la química física. Sus aportaciones han sido cruciales para el desarrollo y la consolidación de la teoría de la estructura electrónica molecular. Otras actividades del profesor Herschbach incluyen su periodo de máster en la Curie House, una residencia de estudiantes en Harvard durante 5 años, con episodios tan curiosos como encontrarse una foca en la bañera de los estudiantes. También quisiera mencionar que el profesor Herschbach está íntimamente ligado con los hilarantes IG Nobel Prizes, en honor a Ignatius Nobel, inventor de la gaseosa y parece ser que supuesto familiar de Alfred Nobel. En estas ceremonias se premian trabajos tan sesudos como aquellos dedicados a la aerodinámica de las patatas chip, la levitación magnética de las ranas en el 2000, o el premiado en el 1996, Transmission of Gonorrhea through an Inflatable Doll. No me he atrevido a decirlo esto con todas sus palabras. Lo cual demuestra su fino sentido del humor y su jovialidad. Además, quisiera mencionarles que el profesor Herschbach ha sido una de las estrellas invitadas en uno de los episodios de la serie de dibujos animados Los Simpson. Si ahora fuese capaz de poner esto en marcha, supongo que es aquí. Here? Okay. Ahí va, como pueden ver ahí.
El comportamiento de las moléculas individuales de una reacción química, y ella es la sexy protagonista de la serie de televisión Alias. Con ustedes, galardonado con el Nobel, el doctor Dudley Herschbach, y la vida más
Doctor Herschbach, yo creo que nuestros trabajos no son tan distintos.
Discrepo. Ganador del premio Nobel de Física, el profesor John Frink.
Bien. All right. I guess that this is more than enough for a short presentation. So I better stop speaking now and call to the floor to the last speaker this evening, Professor Herschbach, who will elaborate on the relationship between the Brownian motion along with the fluctuation dissipation theorem, that's part of Einstein's legacy, and the wonderfully arranged motions that occur in a number of molecular environments, including living systems, that's molecular models, his newly brewed research work. Professor Herschbach.
Oh my gosh. You must have found that. Did you find the Simpsons thing? Well, I must say, I'm even more delighted to be part of this wonderful conference than to have appeared on The Simpsons. It is a wonderful conference, and like the other speakers, I've been very happy to be here. It's a joy to come again to the Basque Country and to have the excitement of meeting so many remarkable people. But the thing that most excites me about this conference is all the young people that are here. I think that's the finest testimony to what Pedro and Dr. Galinda wanted to achieve with this meeting. I often think, when I think about the Einstein celebrations this year, that, oh my gosh, is there a danger of sending the wrong message to the people we most want to be inspired by the saga of Albert Einstein? Namely, that Einstein represents the way science must be done. Most of us don't do science in the way that the image of Einstein suggests. Not the real Einstein, but the image, namely the lonely genius who suddenly sees things totally differently than other people and revolutionizes everything. That's one reason why understanding something about the history of science is so valuable. It helps you put things in perspective and see how science actually does evolve. As we just heard in the wonderful talk by Jean-Marie Lane, it's marvelous to see how complex things like human beings, thinking beings, have evolved, and the wonders of self-organization are there for us to be examined. But the larger message for the young people, for the whole symposium, and I think particularly for chemistry, which I would say will probably do pretty interesting things even in the 21st century, let alone the 22nd and the 25th. The larger message is there's so much more to be found out. Many times young people speak to me, they've had the experience of going through wonderful courses that have shown them the great things their previous generations have done in science, and the students clearly have the impression how lucky these people were. They just walked through the orchard, shook the trees, the fruit fell into their hands. We won't have it so good. Do any of you have that impression? Are there any PhD candidates here? But I always point out to them what you have to recognize is the legacy of tools that your predecessors didn't have, tools that literally give you new eyes to see, new ways to think. The STM is a marvelous example of that. And that's the sort of thing I had in mind in thinking about what to say at this meeting. Obviously, we're here to celebrate Einstein, and so I wanted to choose a topic that I thought had particular interest. It wouldn't be as celebrated as, say, relativity, but in the world that Jean-Marie Lane has just described so beautifully, as you heard in the wonderful lecture by Professor Lucas earlier, Brownian motion is a huge thing. It's inescapable. It goes on at all levels. These molecules are going to be banging away no matter what else we large complex systems want to do in the world. But also from the historical perspective, I wanted to emphasize that it wasn't simply Einstein's work that was so important in advancing, as you heard earlier, the appreciation of fact atoms and molecules are real, but it was what was followed up by other scientists, in particular Jean Perrin. So since I always have felt that's not emphasized enough in the saga that students typically encounter in textbooks of chemistry at least, I want to say a bit about that. Then I want to shift to the subject of molecular motors, but on the way there's a nice transition to tell you a story of a high school student I met 6 years ago who's just done something that I think would delight all of you, and I will tell you when I get there, and it will be a transition to move on to molecular motors with reason to approach it in this context is that molecular motors, and particularly enzymes, are the prototypical case, have to contend with Brownian motion, which from their perspective is an overwhelming handicap. As you saw with Jean-Marie, it's a question of transforming randomness into directed motion. That's the enzyme's task. So in a way, that major part of my talk will illustrate an aspect that you heard from Jean-Marie's, what I like to call sermon. So let's see, I think this button, maybe this button. Whoops, no, I did have the right one. You saw twice already this photograph of Einstein. I want to linger on it a moment. Most people probably don't know that he had this photograph taken when he was in the patent office, because he was getting lots of requests for what we would call reprints. And the custom in those days was to supply the person who requests a reprint a photograph of you. So he posed for this specifically. But it's appropriate, of course, because it's of the time we talk about, the year we're celebrating, the miraculous year of 1905. But I think, especially for students, I should add a little, in the way of background, how did this guy wind up sitting in the patent office? Do you know enough about Einstein before he was Einstein? At a symposium in Berlin this January, where I was invited to talk, I saw they were going to have philosophers, musicians, artists, all talking about the impact of Einstein. But it looked as if nobody was going to talk about Einstein before he was Einstein. So I talked about Einstein as a student, and with some help, as you might well imagine, from Professor Jerry Holton, who you'll hear about, I think, on Thursday. I learned more than I knew before about Einstein, and some of it I think all of us should know. For one thing, Einstein very early, as you might expect, developed a passion for science and mathematics. But that didn't mean that his path to success, or even to the PhD, was a happy and smooth one. It was very rough. Some of you know, I presume, that he was a high school dropout. When his parents moved from Munich, where he was a student in the gymnasium, he felt very unhappy to be left behind to finish his last year in the gymnasium. And without his parents having any idea, he negotiated with the family doctors to get a fictitious medical condition testified to, so he could escape from the gymnasium, which he disliked because the teaching methods were so authoritarian and regimented. And he appears in Milan, where his parents were, to their great surprise, and they were upset because they had hoped he would go on to college. He said, "Don't worry, I'll study on my own." And he did for 9 months. Then he took the entrance examination to the Swiss Federal Polytechnic, now known as the ETH in Zurich. And he was very confident he would pass and be admitted as an engineer. It was mainly an engineering school. He failed the exam because his general knowledge was not strong enough. But he did well enough in math and physics that he'd studied on his own, that the director of the ETH suggested he go to a small school nearby, Aarhus, that had arrangement where any graduate immediately got admitted without a further exam. He did that. It was his one happy academic experience. At the ETH, however, he found the courses very disappointing because he wanted to learn theoretical physics. So he cut most of them. And he was rather snooty to his professors, making clear they weren't teaching what he wanted. In fact, he spent most of his time, by his own testimony, when he was at the ETH, in the laboratory, because he thought then, as he said, that the way to make major progress in physics was through experimental observation. Well, to just jump ahead quickly, when he graduated, he had enrolled in a section to get a high school teaching diploma in physics and mathematics. He expected, since he by then had decided to go on for a PhD, that he'd be appointed as a teaching assistant, because there are 800 engineering students and only typically half a dozen or so graduates in mathematics and physics then. So that anyone who wanted in math or physics to be a teaching assistant was automatically. He was the one exception in the year he graduated in 1900. So for the next 2 years, he could barely scrape together through tutoring and temporary jobs a way to live. So all of that is what led to the patent office, because through a college friend's father, he was steered and managed to get that job. It was a very, very happy job. He liked it immensely. And he said, look, I only have to work 8 to 5, 6 days a week. That leaves me plenty of time to study the science I want to on the side. Well, of course, there's no way to understand how he burst forth in 1905 with those remarkable papers. But again, from a historical perspective, you can get some clues. First of all, he had already published 5 papers before 1905. The first 2 embarrassed him later because they were based on very naive ideas. The next 3 he really had for himself recreated a lot of what Boltzmann and especially Gibbs had done in the statistical mechanical approach to thermodynamics, which he built on very much in 1905 and some of his later work. So it wasn't entirely that. But I'll touch on maybe a couple other points, but I think I should move on now quickly to saying something about the Brownian motion. Here's a Dover reprint that has the 4 papers Einstein published that we regard as dealing with Brownian motion. We celebrate so much. The second one, actually, is not specifically about Brownian motion. It's his PhD thesis. We'll say more about that a little bit later. You heard from Professor Lucas quite a bit on that score. But I just want to mention that because I always like to point out things that students can look for. The opening sentences, I think Professor Lucas mentioned, that the very first sentence Einstein says in the paper that's called a Brownian motion paper, which was sent in only 11 days after he completed his thesis, more about that later, which he says, it will be shown in this paper that according to the molecular kinetic theory of heat, bodies of microscopically visible size suspended in liquids must, as a result of thermal molecular motions, perform motions of such magnitude that the motions can be easily detected by a microscope. So he recognized and emphasized right away the key thing that you had here, the connection that this microscopic motion of molecules that we had no way then to observe had this observable consequence that it ought to produce observable motions. He commented then, which I skipped, that he didn't know whether that really was what people referred to as Brownian motion because he himself didn't have access to the right data. But later he emphasizes the consequences of this. A sentence or 2 later, if it can actually be observed, he felt that classical thermodynamics would then be shown not as applicable even to bodies you can see move microscopically. That had to do with conceptual controversies of the time that Professor Flores referred to. And then on the other hand, he says, as the prediction of this movement, the Brownian motion movement, failed to be, proved to be incorrect, it would, of course, disprove the molecular kinetic theory of heat. So he was alert to the major consequences. Now, you all know the notion Brownian motion produces these jagged pictures, This is one actually from Jean Perrin's work, but the reason I show it here to remind you is that one misconception that hampered previous recognition of what was going on was that people had the idea you can measure the velocity by taking the distance traveled and the time it took. And here are snapshots at 30-second intervals. You get this irregular business. If you try to work out the basis of velocity and the energy involved and so on, you get total nonsense. You'll see how Einstein's view cleared that up very shortly. I just want to emphasize, if, as Perrin did and emphasized in his own work, if you take the same pictures of the motions, these are looking at granules, colloidal particles in a microscope, which is a very laborious thing to do back then. They have to do photographically and all and then count them. If you take them a shorter time scale, you get the same kind of jagged pattern. It's something independent of the time scale. And that seemed a mystery as well. So that gives you a little bit of a flavor. Now here's the dissertation. About that, I'll just say, I mentioned that he completed at the end of April. It's a curious thing because he didn't turn this in as his PhD dissertation until near the end of July. Why? Well, he had had some prior experience. I think current students might want to know that Einstein had to try 5 times to get a PhD. In fact, I would predict he wouldn't make it today, but that's another story we could elaborate on. The first time was after he graduated from ETH. Even though he didn't get a teaching assistantship, he continued work with a very professor who had disappointed him, Professor Webner, and not appointing him as a teaching fellow, to try to complete a PhD. In those days, you expected to do a PhD within 2 years of having graduated from college, because a PhD consisted of 1 manuscript that was judged a competent scholarly contribution. He had done what's called a Diplomarbeit, or the undergraduate thesis, with Professor Weber, and as often was done by students then, he thought he could enlarge on that and complete his PhD, he thought, by the spring of 1901. It was an entirely experimental thesis he intended to do. As I mentioned, he's done mostly work in the lab during his college years, and he liked it. He, however, abandoned that from a fallout with Weber, which he thought prejudiced his hopes of finding another job. So as I say, for the next 2 years, he had a miserable time. He wrote letters that all failed to be even responded to try to find other jobs until he wound up in the patent office. But in this thesis, well, I should mention, he tried one other, submitting another thesis to the University of Zurich, which was rejected. Then he tried, after he was in Bern in the patent office, when he learned that there was, in the University of Bern, an option to become a privat docent without a PhD, and he'd published by then 4 other papers. He submitted them. That was rejected. And then I think, although it's not quite clear in the historical record, the reason he didn't turn in this thesis when he finished it in April 30 was he had a better idea, he thought. And according to his sister, he submitted his special relativity paper, which he finished in June, 5 weeks after this, and that was rejected. It had no obvious connection to experiment and the professors, and they didn't understand it either. So then finally he submitted this one, which did have experimental pertinence, because as you heard from Professor Lucas, he showed in here how to connect diffusion and viscosity. And he got 2 equations from which, as his title emphasizes, he was especially interested in a measure of the dimensions of a molecule. He got that, and he got a measure of Avogadro's number. Those were, he recognized, something that with a little elaboration, he could apply to this Brownian motion problem. That's what he did in a paper 11 days later. I put this in wonderful biography by Abraham Peiss, because those of you who want to look in to this whole story more deeply will find it an excellent place to go. Now, here is my little bit of theory, but I can be very quick because you've heard it from Professor Lucas and also Professor Flores. The hero of the problem is, of course, the diffusion equation. Let's see if this is a laser pointer that I can find the right button for. I haven't found it yet. At any rate, if you recognize already the diffusion equation, he was interested in the number of particles per unit volume, neighborhood of position x time t. He had in his thesis this relation of the diffusion coefficient to viscosity, particle radius, which came from Stokes' law. Oh, how clever. Thank you. Yeah. No button needed. Yes. A buttonless projector. Fine. And you've seen this solution to the diffusion equation. Incidentally, you can recognize from dimensional analysis that it has to have this form with an x squared down here, t over there. The diffusion coefficient must depend on a square of a distance over a time to make that dimensionlessly correct. So that's what happens when the combination when you solve this thing. And you could combine that, because he had this expression for the diffusion constant with a previous one, and get this all-important one that connected the the average of the square displacement from the original position. You could take it 0 for each particle and sum over all of them, to time, and it goes linearly. The square goes linear with time. That means the displacement goes quadratically with time. That means you can't define a velocity in the way people had tried before, because that's not a distance over time. It's the square root here will give a distance, and it'll be over a square root of time. So that's something key. And then, of course, it relates it to the size and the viscosity, things that can be measured separately, the temperature, Avogadro's number, all the rest. In a later paper sent in December of 1905, he extended this to rotation, and essentially it's almost the same argument. You notice the cube of the radius comes in, because for rotation it's the volume that matters, not just a lever arm or linear dimension. He also later extended it in a paper the next year to the action of gravity, which I'll mention and allude to later. This is a plot that shows that equation, how the time development or the displacement goes with time. In a linear scale here, you'll see that to get the same net root mean square displacement, you have to, of course, go twice the time. So this is in measurements of 4, 16, to show the expansion of the particles. Finally, I put this in because Jeremy Bernstein, a wonderful science writer, has just published in American Journal of Physics this interesting historical note that 5 years before Einstein, 1900, the very year he graduated from ETH, a thesis had been published by a French mathematician. Einstein certainly never knew about it, maybe even for his whole life, who actually derives the same key equation from the amounts of the diffusion equation, except that the displacement corresponded to price. And he applied it with modest success to the stock market. Now, that's okay for analyzing fluctuations, but as we all know, that's not the important variable when it comes to the stock market. But that's only a comment by way that there were many others involved in this that have interesting connections. I think because of a constant to the square root of time, I will hasten on a little bit. But here's a historical sidelight. One thing that Einstein had done during the time he was in Bern before he got his patent office job, hoping any day, was offered to tutor people, and this led him to meet a young Romanian student who wanted to learn something about physics, even though his background was in philosophy, Maurice Solovin. And they were soon joined by another, and they formed what they call Olympia Academy. And they read widely, and one thing they read very studiously was Poincaré's Science and Hypotheses. And even though Einstein, which they read in 1904, it came out in German translation, and they read it for weeks, according to Solovin's testimony. And here it has this comment which almost mirrors part of what Einstein said. He may have forgotten about it in the heat of creation in May of 2005, but it was something I'd explore if we had more time. Now I want to mention, as I say, the work of Jean Perrin. The PhD thesis of Mary Jo Nye, a now distinguished historian of science, dealt beautifully with Perrin. Here he is at his microscope, very different than your microscope, Heinrich. This is a magnificent book he published in 1913, collecting all of the work he did pursuing Brownian motion. I will show you what his apparatus was like. It's nothing but a little grooved plate here. The depth here is less than a millimeter. He could focus his microscope objective so that the depth of field was such that you'd see just a very narrow horizontal slice. And then he would change the depth of field, move to another horizontal slice, and then he'd make other measurements looking in the vertical distribution of these emulsions of particles distributed in water. And he did lots of hard work to master making particles of a known radius. How did he know their radius? Very clever ways, getting them to stick to the wall so he could count hundreds, thousands of particles and measure the area, and that way get their size. He did many neat things. He confirmed that Stokes' law, which Einstein had assumed, still held for particles of the size he was concerned with, say 1 micron in Brownian motion, but which of course had only been established for macro kind of particles before. All these things Perrin did beautifully. Here's a bit of his data showing that it really was random. Here's his test of the square root law. I mention all this because as I said to Jean-Marie the other day, I really think every serious student of science, physics or chemistry, ought to read Perrin. It's such a magnificent saga, how with the limited tools he had, he could do these amazing things. After all, transforming, witnessing in the microscope something with your own eye that was your best evidence then for the existence of atoms and molecules. And here he collected several of them for different methods he used. Avogadro's number, there's a systematic bias then, but in the scatter, as they could determine it. And he finally triumphantly ends his book with this statement: atomic theory has triumphed. Its opponents, which until recently were numerous, have been convinced and have abandoned one after another the skeptical position that was for a long time legitimate and no doubt useful. I love that last phrase. It's a very decent and fine way to acknowledge the role of controversy in science, which is absolutely crucial to progress. And then he adds another paragraph I couldn't resist, given that we will have and have had already marvelous reference to cosmology. He writes, "The feeble light from Milky Ways immeasurably distant tells of the fiery life of 1,000,000 giant stars. Nature reveals the same wide grandeur in the atom and the nebula, and each new aid to knowledge shows her vaster and more diverse, more fruitful and more unexpected, and above all, unfathomably immense. All right, now from there I go to my high school student, now a first-year graduate student in the Department of Physics at Stanford, Adam Cohen. I couldn't resist this story. I think you'll see why in a moment. You see the title of his paper, Method for Trapping and Manipulating Nanoscale Objects in Solution. I say he was a high school student. Well, that was 6 years ago when I met him at the Science Talent Search I've taken part in for many years. He won first place by building a scanning tunneling microscope for $50 in his bedroom and doing some nice work with it. I see Heinrich smiling. Then he came to Harvard as an undergraduate as a chemistry major, and deciding that physics had some relevance for the 21st century, he thought at Stanford he would get a physics degree. But since I think you may not be able to read, I'm going to just read the abstract here. We present, this is with W.E. Murner, his faculty advisor, we present a device that allows the user to trap a single nanoscale object in solution at ambient temperature and then to position the trapped object with nanoscale resolution. What about Brownian motion? What about it? Well, the next sentence reads, this anti-Brownian electrophoretic trap, they call the ABEL trap, you know from the Bible who they're referring to, works by monitoring the Brownian motion of the particle by fluorescence microscopy and then applying a feedback voltage to the solution so that the electrophoretic drift exactly cancels the Brownian motion. The ABEL trap works on any object that can be imaged optically and that requires a charge and acquires a charge in water, and there are many, many such things. The ABEL trap works on, the ABEL trap is non-invasive, is gentle enough to handle biological molecules, and can trap objects far smaller than can be trapped with laser tweezers, which we will speak about shortly. Our proof of principle device can trap fluorescent polystyrene nanofibers with diameters down to 20 nanometers. They think now they'll soon be down to 1 nanometer. Now, you see why I wanted to put this in here. This is what it looks like. It's not a heck of a lot more complicated than Jean Perrin's apparatus, right? They have these electrodes. By observing the fluorescence and using computers, these new tools that Adam Cohen had available that weren't even available in this combination even 10, 15 years ago. They applied these potentials, and they're able to create patterns to make these little things instead of just succumbing to Brownian motion, make what they want. For example, here's one thing they did. This is a rather easy case for them, a 200 nanometer particle. In 1 minute, they made this smiley face, steering it around. And they can do the same with all sorts of things. Now the laser tweezer, now the transition to molecular motors. There's no better summary, I think, and so I made this scan of a paragraph from a paper by my friend Dean Ostumian and his colleague. There's no better summary of what's the connection to Brownian motion and molecular motors than this one, and you'll see it illustrates in a particular way the broader themes that Jean-Marie was emphasizing and also Heinrich. To put the magnitude of the thermal noise that any enzyme or molecular motor, so-called, that's going to do a job in solution at typical temperatures in perspective, consider that the chemical power available to a typical molecular motor, which consumes about 100 to 1,000 molecules of ATP, that's the fuel, the universal fuel for biological processes, is 10 to the minus 16 to 10 to the minus 17 watts. In comparison, a molecular motor moving through water exchanges about 4 times 10 to the minus 21 joules. That's the thermal energy, Boltzmann constant times the temperature, with its environment. And it does that very quickly, 10 to the minus 13 seconds. So you take that energy, divide by the time, and you find that the thermal noise is about 10 to the minus 8 watts. That's far greater than the chemical energy, or the chemical power, the 10 to the minus 16, 10 to the minus 17 watts available to this chemical motor. They go on to say, for molecules, moving in a straight line would seem to be as difficult as walking in a hurricane is for us. Nonetheless, molecular motors are able to move, and with almost deterministic precision. There's this long history of enzymes. They were often, early on, regarded as total mystery. Vitalism was a real word in biology. It was enzymes did these marvelous things. We didn't understand the mystery of enzyme catalysis. Well, you see, even to think about how they can be deterministic in the face of Brownian motion is a very striking episode. Here's a very nice figure I particularly should put on, because Felix Retort is from University of Barcelona, but his excellent review just came out in Physics Today with Carlos Bustamante and Liphart as co-authors. It shows the dissipation rate, that's again in joules per second or watts, and compares motors of various kinds, the kinds we're used to up here, and these molecular motors. Kinesin is a favorite one, for example, way down here, and the same basic point that just made previously in words by Ostumian. Now, one way to think of how it's possible, despite Brownian motion, for enzymes to operate is the Brownian ratchet picture illustrated here. If you imagine that the potential energy that the system has to work against is like climbing up a hill to accomplish some work. The enzyme needs to accomplish work to make whatever chemical phenomenon happen. Well, that's an uphill thing. If you imagine, however, the shape of the potential happens to have this kind of shape, whereas a gentler slope on one side than another, and if that, you imagine, can fluctuate on and off, and there's certainly lots of molecular motions that would do something qualitatively somewhat like this, then you can see how Brownian motion can actually foster uphill travel. If it's off, you expect things to diffuse more or less equally. It would be biased a bit, just as in a gravitational field Einstein showed us. It wouldn't be quite equal upstairs, down and up, but roughly so if it's not too big a disparity. And then if the sawtooth thing comes up again, you can see that more stuff would have gone in the unfavorable direction than in the favorable. And so you get more stuff winding up trapped over here, because it would slide down into this minimum. So you can see how the things can work uphill. And another lovely article I recommend to students, a Scientific American article, Dean Ostumian, has the example of trying to run a car uphill in a fierce hailstorm. Of course, the hail has to bombard very vigorously, but if you adopt your parameters correctly, you can imagine the mass of the car and so on, comparable to an enzyme molecule working against Brownian motion, and pumping the brake. And the net result is similar to what was just illustrated. Well, now now here's a poem that was included by Dean in his paper. I couldn't resist. I thought at this point people would like to hear a poem. We could come back to it, but I'll just read the first line. Let the place of the solitaires be a place of perpetual undulation. And that just emphasizes that's what we all face for Brownian motion. But now let me go on to the last episode I want to explore. It has to do with molecular motors, a prototypical case that illustrates the kind of thing that's been done for quite a few systems now. And as you'll see, it has another connection to Einstein. Here is a sample of a so-called laser or optical tweezer experiment, the sort that was mentioned in the Cohen and Molnar article. If you glue a piece of DNA to a polystyrene ball, and there's ways to do that, two polystyrene balls and glue one polystyrene ball to a pipette, and the other one you trap in a focused laser field. You can exert a force on this DNA. First, think of it as just a pure strand, single-strand DNA. And you can measure the extension as a function of force. The force is measured in nanometers, in nanojoules. And if you aren't familiar, the force is measured in piconewtons. I've heard so many nanos, I have trouble not using that word in front of other words. If you want to know what a nanonewton feels like, remember how it feels to have a mosquito land on your hand. That's a roughly 1 piconewton. I said nano, I meant piconewton. And here's the force, the fractional extension of the single strand. You see it stretches pretty easily. The double strand is much stiffer, but at a certain point, of course, it gives up and unravels and rapidly moves over and behaves like single strand when you get above around 50, 60 piconewtons. So those measurements have been made. And now what we're interested in is the molecular motor situation. That refers to a typical experiment where you have an enzyme that's represented by this little thing here. It's a small, teeny thing compared with, say, 10,000 base pair strand of DNA, which is typically what would be used in such experiments. And it works its way along. All of this is in solution with the kind of bases that want to add to, the enzyme wants to add to the single strand portion to convert it to double strand. And actually, one can measure with a lot of scatter, as done in many laboratories, how the rate of replication, the addition of the bases, changes with the tension applied to the DNA. And you see it goes up a little bit maybe and then comes down steadily. And this is regarded as a measure of the work that the enzyme has to do against the tension, which is slowing down its enzymatic activity. Now, a lot of experiments have been done in this area, and this particular one and several others like it reached a conclusion I couldn't believe. I couldn't believe it because as a chemist, I'm always interested in structure. The conclusion I couldn't believe was they analyzed the data in such a way that they concluded that in what chemists call the transition state, that's sort of the key region through which the system passes in the way from reactant to product, there must be 2 nucleotides involved, even though from other studies we know only 1 nucleotide is incorporated in each catalytic cycle. You add 1 base at a time as this molecular motor enzyme works its way along the DNA. But this interpretation, which was a physicist's interpretation, if you excuse me teasing physics a little bit, went like this. It came about this way. They're applying a known force. Work is force times distance. So we get an idea of the work done by the attenuation of what happened in that curve you just saw. So that gives an idea of what the key distance involved must be. And that distance corresponded about to twice the change in the spacing between residues in single strand and going from single strand to double strand DNA. As you go from single strand to double strand, it shrinks, and this is twice that shrinkage. So that's why I concluded 2 must be involved. Another study on a different enzyme concluded maybe 3 or 4. Well, structural studies have been able, in some cases, this one here, to trap DNA interacting with an enzyme. The blue goop there is really the background of an enzyme. Roughly speaking, has the form of a right hand. It's an open configuration, as we like to say, with a piece of DNA stretched across. And then when the enzyme operates to try to convince the DNA to do what it should and incorporate another base, it closes, in effect. The finger structure closes, kinks the DNA a bit. This is, you see the single-stranded portion on one side just a little bit of it. It's hard to resolve in X-rays, and the double-stranded. There's really only room for one new base to come in what's regarded as the critical configuration. So we proposed a simple model as chemists that instead of thinking about changes in the spacing, the covalent bonds, which are stiff and hard to change, think about changes in angles between open and closed. And we just looked at the two segments nearest the active site, which is labeled 0. That's where the new nucleotide's going in. And we were able to show that we could account for the data just as well. Well, that was not at all a satisfying model, and so we went to what is a very powerful and welcome tool available now to the younger generation. Martin Karplus and his group have been foremost in work in this area, the biological area, molecular simulations, and a wonderful Romanian postdoc of his carried out the main part of this work. And so we modeled this very process I've talked about, and I can finish very quickly. I want to show you just two things about it, and then we'll be done. Before mentioning applying tension, I'd like to show you, just leaving out all the enzyme except this part in blue here, which is an alpha helix plus one other tyrosine group. What is a very charming situation, gives you some feeling for life at the level of enzymes. What you see here is a part of the already accomplished double helix. In yellow is the incoming nucleotide, the base that wants to form a Watson-Crick pair to one of the residues on the single-stranded portion of the DNA that's waiting for it. But in the open configuration, something funny happens. A part of the enzyme, this blue group called tyrosine, is sitting in the church door. Moreover, the groom, as I like to call him, the Watson-Crick base that wants the hydrogen bond ultimately with the incoming bride here in yellow, is taking a snooze. It's laying flat over here. What happens when the enzyme closes? That's what the ATP energy allows. It's a modest little thing. That modest thing moves ominously this alpha helix up, but that rotates this tyrosine thug out of the church door and flips the groom up into what I like to call nuptial alignment and allows the base pairing to occur. So this gives you an insight how a modest little chemical energy, despite all the wildness that goes on in molecular environment, can catalyze base pairing. And as so often happens when you look around in art, you discover that Chagall, back in 1917, recognized the phenomenon of nuptial alignment as terribly important in weddings, whether they're human or molecular. I'll just mention very quickly, because I want to make the connection to Einstein, one of the people who helped, as well as Perrin, sort of publicize and make people aware of the value of Einstein's Brownian motion work was Langevin, who in fact reformulated it and published the version that's usually in textbooks now, rather than Einstein's original one. But here, this is a weighted kind of averaging. Long ago, back in 1913, Langevin and later Debye used it to discuss the orientation of molecular dipoles in solution when buffeted by the thermal environment. And so you have a weighting that depends on the interaction of an external field, that's this F with a dipole moment mu. That's a weighting, like gravity would in the gravity case, for example. And of course, whenever someone works out a simple thing, gets a beautiful little formula, this is what it looks like. It shows that the ratio of the interaction energy of the dipole with a field compared with Boltzmann constant time T, which is really the measure of the thermal energy that the environment is buffeting it with, that's what governs the degree of orientation you can get. Well, it's very, very modest under ordinary conditions. But actually, polymer chemists long ago have taken over this same model. I wanted to mention this because it shows students how old, simple, basic things get reincarnated all the time in new contexts. And you may find, if you want to pay some attention to history, that you find opportunities to do that in your own work. So in polymer chemistry, you often have your system subjected to strain in the flow, or in the experiment we're discussing in a moment, tension applied by this new technique of laser tweezers. And it's customary, first for flow problems and now for this one, to essentially adopt the Langevin thing. It's the same story. You think of the polymer made of as various segments that have to orient, and so the dipole moment plays the role of one of those segments, called often the Kuhn length or the persistence length. The electric field is emulated by tension. Well, with that formula, and this is my last, almost last few graphs, what I show here is experimental data for a single-strand DNA, and the green curve is what you'd get from the Langevin-Debye formula. There's a double strand. And these are the simulations. And of course, they're totally different. Shows that the idea, which was what we used before, of taking this data and trying to interpret changes in length and so on, isn't right at all. What you have are changes in angle, but the basic picture is so simple now. You don't have the whole range of angles accessible. What the enzyme does is limit how those segments of DNA can wobble around. It restricts them. And so if you do a little model, the same as Langevin, but instead of integrating from 0 to 180 degrees, integrate between some maximum and minimum that's set by the geometry of the enzyme, you get these red curves. They're a very simple model. So that's actually nothing much more than something very akin to Einstein's treatment of Brownian motion with added restriction akin to what he did with gravity. I just wanted to finish by advertising this website from the Center for History of Physics. American Institute of Physics is something that Jerry Holton and I have both been involved with for some years. And they give, as you can see, segments on all of Einstein's career. That's very fine indeed. Well, I have exceeded a little the square root of 2, square root of time. And I know you're eager to get off to dinner. So I would just like to finish by quoting a favorite physicist of mine. I think it fits in with what you have heard this evening and earlier, and we'll hear later at this meeting. Feynman said, "Science is not about what we know," even though we celebrate so much wonderful science that we inherit. He said, "Science is about what we don't know." And you have a great opportunity in the coming generation to find out quite a lot more about what we don't know and to show us still more that we don't know. Thank you.